Welcome everyone to a brand new AI Research Bite. Thank you so much for joining us. My name is Marie-Lise and I will be your host for this session. For those of you who are new here, AI Research Bites is a series of short, informative talks where we showcase cutting-edge research from ServiceNow's AI Research team. These sessions are open to everyone, especially those of you who want to stay connected with the fast-moving world of AI research. Today's session featured a 15-minute talk from Hadi Nekoei, and the presentation will be followed by a 10-minute Q&A. Before we dive in, let me share a few words about today's speaker. Hadi Nekoei is a visiting researcher here at ServiceNow AI Research. He's currently doing a PhD in computer science from University of Montreal and Mila. His research focuses on generalization and adaptation in machine learning, with a focus on multi-agent systems and memory-augmented LLM agents. Hadi's research is supported by NSERC and FRQNT. With that, I'm thrilled to hand things over to our amazing speaker. Hadi, the floor is yours.
Thank you so much for the introduction, Marlies. I hope you can see my screen.
Yes.
Okay, perfect. Okay, so let's get started. Today, I want to talk about the Jeffinter, which was our recent project at ServiceNow AI Research, which is basically about a memory augmented approach to fine-tuning your LLM agents without really fine-tuning them. If you're interested, you can find the paper on arXiv by scanning the QR code. I will keep the QR code at the end of the presentation as well. So just a quick disclaimer, this is an ongoing research, whatever is presented here. Sorry. Okay, so as you all know, like LLM agents are starting to do a lot of our daily interactions with the computers, and they are kind of working, but the thing is they are still failing in unfamiliar domains, mainly because of not being able to reason properly with new in unseen tasks. And they can also be unreliable, mainly because of the hallucinations that they have when they face new domains. So there are existing solutions, for example, updating the weights of your LLM agent with reinforcement learning or supervised fine-tuning. This can be too costly for open source models and impossible for closed source models because we don't have access to the weights of the models. At the same time, these approaches can result in catastrophic forgetting, which means that when you learn something new in your domain task, the LLM agents will forget the knowledge that it had about the other tasks. Another family of approaches, which is around like retrieval augmented generation methods, they are about basically retrieving the most relevant interactions of the agents that previously it had with the tasks and try to replay them while the agent is interacting with the current task. But the thing is, like, as we are getting into the domain of more and longer horizon tasks, these raw replays can be quite noisy, and the agent can be actually confused by adding these replays to the agent. So the questions that we asked was, can we design a mechanism to learn from previous experience without fine-tuning the weights of the model or relying on a noisy RAG approach? So let me try to explain our approach with a simple example. So here we have a work arena sort hardware list task, which is basically about sorting a list of items by like a specific column. For this specific task, we have the goal of sorting the hardware list by eligible for refresh column and due column, and both should be ascending. What agent does by default, it will add these columns because it wasn't already part of the list, and it starts to sort these items by clicking on the headers. But the thing, what happens is, like, when the agent sorts the second column, the first column that was sorted gets unsorted. and then it starts to sort the first column again, and the agent gets stuck into a never-ending loop of sorting one column and then sorting another column. So now to solve this task, what we found was that just by saying a simple hint to the agent, basically adding this hint that use the filter panel to sort multiple columns instead of clicking on headers, uh, the agent were able to directly go and use the filter panel first of all, and the rest of the actions the agent is already capable of doing it. So basically, as you can see here, the agent opens the filter panel. Now it needs to add another two sorting criteria. The first one for eligible for refresh. So it already adds the eligible for refresh. For the due column, it clicks on the add sort, and it will enter the due in the field. And because these columns are already sorted A to Z, the agent really doesn't need to do anything else other than just running the filter, and the agent successfully stopped the task. So as you can see, like what the agent needed to know basically was just that for this specific platform of Work Arena, it's better to use the filter panel when you want to sort multiple columns instead of playing with the headers. Okay, now the question is like how we can extract these uh, hints, ideally short hints, and also being useful. So that's where Jeffinter comes in. So Jeffinter is basically about turning messy offline traces into clean and reusable guidance. And how it works is basically we have a hinter agent which looks at the traces of the base agent and converts them into the hints. And these hints are stored in a hint database, which is going to be retrieved by the agent at test time. A bit more concretely, let's say we have some trajectories from the previous interaction of the agent with the tasks. Some of them can be successful, some of them can be failures. Um, uh, our hinter agent uh, goes and looks at these traces and tries to find the most important steps in each trace. And by creating like a structured prompt of what happened in the first case, what happened in the second trace, it tries to reflect on these steps and generate a hint. And then these hints are saved into a database with alongside a semantic key, which is basically a short summary of the situation that the agent were in. And then when we finalize this hint database at test time, what agent needs to do is only basically retrieve the most relevant hint for the given task. So, and it does that by basically comparing the embedding of the current, like let's say we have a query for the current situation, we compare it with the semantic key in the database, and we retrieve the most relevant hints. If we know the task ID, that's much easier. You can just grab the hints that are related to that specific task and retrieve the most relevant hints. So the key innovation here is that this zoom and reflect pipeline, it really finds the most important steps that was either the failure points that the agent couldn't solve the task, or it was a successful trace and the agent tries to summarize this to a hint that would help the agent to repeat those patterns more reliably in the future. Okay, so let's see how Jeffinter compares with the previous related work. So two most important and related work that we had was first one is Agent Workflow Memory by Wang et al., which basically what it does is it looks at the previous traces and only generate the workflows from successful trace. As you can see, the limitation of this approach is that if you don't have any successful trace for a task, you won't get any workflow. So in that sense, it cannot learn from the failures. Another work which is also very relevant is AutoGuide by Fu et al. What this work does is basically um, instead of limiting to successful traces, it looks at the pair of successful and failure pairs. Um, it's still limited to the cases that you at least have one successful trace, but at least the agent can compare the successful and failure traces and try to generate hints that would help the agents to avoid the failure scenarios. Um, but the thing is with AutoGuide that the hints are given stepwise, and this stepwise guidance means that at every time a step of agent interacting with the task, you need to add an LLM call to generate a query for each step, and then retrieve the most relevant hint from the database for that specific step. And this makes the AutoGuide very quite expensive at inference time. In comparison, like Jeffinter generate episodic feedbacks from offline traces, and it does it by zooming on critical steps. This means that the agent only retrieves the hints and in the beginning of the episode, and it makes it super cheap at inference time. So it means just one simple retrieval step. And also, Jeffinter can learn from both successful and failures. So even if all traces are failed, the agent still generate hints for those scenarios. So, like a short summary of our results, we tested Jeffinter and AutoGuide and the React baseline on three standard benchmarks of web-based navigation and like enterprise task of work arena and like a mini web. And we see that Jeffinter, which is the red line, is able to improve the average reward compared to React agent, which is the baseline, while adding very minimal inference cost. On the other hand, like AutoGuide also improves the performance a little compared to React, but the cost that it adds at inference time, it's much higher than Jeffinter. Another aspect of this, the evaluations that we were interested in was to see how generalizable the hints are. And we had like an interesting mix of results. On Work Arena, we observed that Jeffinter can generate hints that generalize to new tasks that the agent has never seen when generating the hints. But on Web Arena, this wasn't the case, and the improvements were mostly within a standard deviation of the baseline. So this can be explained by the fact that Work Arena, different tasks in Work Arena sometimes share the same patterns and same style. So the agent was able to generate the hints that would generalize. But this isn't the case for Web Arena because the Web Arena is basically solving tasks in different websites. So this could be a very like interesting future research direction to how to make the hints generalized to unseen tasks. Also quickly, like looking at like a qualitative analysis of how these hints were useful, we looked at like the effect of zooming mechanism, and we found that this zooming mechanism is actually very important. It can isolate the minimal causal workflow behind the task solving the task, and like by zooming on the most important steps in successful and failure traces, it was able to generate a clean and like structured hint. On the other hand, without zooming, the generated hint was mostly unfocused and it didn't help. At the same time, zooming become more essential as the tasks become more complex and long horizon because it's hard to fit all the steps of a trajectory inside the context of the hinter model. So we need the zooming mechanism to find the most important steps. Okay, so finally, as key takeaways, why Jeffinter is important. So Jeffinter is designed to be efficient and also interpretable compared to like standard supervised fine-tuning or RL methods. You can go and see which hints were useful and even like what was the sources of the hints and which traces were used to generate those hints. So this can help you to understand how these hints is really helping the tasks. The Jeffinter idea is basically distilling offline traces into context-aware hints with zoom and reflect pipeline. And in terms of like future work, the one aspect is like refining the hints. So in the Jeffinter paper, we only did like a zero-shot generation of hints, but you can think of like having a like iterative process to refine the hints as you evaluate them in the environment. Another interesting future work, as I explained, could be like to think how to make the hints more generalizable to unseen tasks. For example, you generate a hint on sorting tasks, and now how it can help the another task in, for example, filtering another filtering task. Okay, thank you so much. Again, if you are interested to know more details, you can find the paper on arXiv by scanning the QR code. Thank you so much, and I'm open to questions.
Yes, thank you, Hadi. Thank you for your great presentation.